Hello and welcome. Today I will be doing a derivation of the Lagrange multipliers equation using algebra, so it's an algebraic derivation instead of geometry. So I used ChatGPT to help me figure out how to do this, and we'll see what it has to say first. So in the next 3 slides, we'll see what ChatGPT has to say about this derivation. And I use this to make my own derivation, and you'll see what I mean. Alright, so basically I asked ChatGPT nicely to do a proof in multiple dimensions. So at first I asked it for a proof of Lagrange multipliers in, for 3 dimensions. Then I wanted to generalize it. So first we start off with the problem setup, and then we do parameterization in multiple dimensions. Then we give it a new function in terms of fewer variables. Then we differentiate f tilde. Then we use the constraints. Then we substitute it back, and then we have the conclusion. So that is the proof right there, and yeah. However, not all steps were explained clearly, as you may have seen, and there were also a few errors, especially with indexing. So I'm actually going to come up with my own version. So the following presentation will be based on my interpretation, or my own explanation, based off of that answer. And you'll see that mine is better. So the first step in finding the extrema of a multivariable function is to set the gradient to 0. So for a function f of x, where x is the vector of x1, x2, all the way to xn, we want to find x bar that is a member of all x's such that the gradient of f of x is the 0 vector. And so we could say that for each element. So what we want to do is, in this case, maximize/minimize xn plus 1 is equal to f of x, subject to g of x is equal to 0. Now g of x, g is a set of equations or constraints, and it is a function of the vector x. And we're going to say that's equal to the 0 vector. Now, let's focus on the constraints. Effectively, what these constraints do is make certain variables in the domain dependent on the others. For example, if we have g1 of vector x is equal to 0, then that could imply that x1 is equal to a function. But if we define multiple variables, then we could combine these constraints such that we reduce the dimensionality of the input to that of the rest of the variables that were not defined as functions of the others. So for example, the example is on the next slide. So for example, if we have 3 constraints, we could say that x1, x2, and x3 are functions of the rest of the variables, functions of x4 through xn. And we could do this through some algebraic manipulations. So we can actually generalize this concept such that if we have m constraints, then we can express m variables in terms of the n minus m other variables. So for simplicity, we'll actually assume that the first m variables are the independent ones, and the last n minus m variables are the dependent ones. Alright, so we have g of x is equal to 0. Therefore, we can say that x m plus 1 is equal to a function of the first m variables, and so is x m plus 2, all the way to x sub n. So those are the dependent variables, are functions of the independent variables. So we have the dependent variables, and we also have the independent variables in yellow. So let us now create a new function, f tilde, that will be the parameterized version of f. So f tilde of x will be equal to the function of the first m independent variables and the last n minus m dependent variables. So essentially, f tilde is the function that we want to optimize. So we're going to set its gradient equal to 0. So in terms of its components, the ith components, or the ith derivative of f tilde of x is equal to the partial derivative of f of x with respect to xi plus the summation right there. For I is 1 to n, and j is summed over the d. Alright, so that implies that that stuff right there is equal to 0. So we can now solve for the partial derivative of f of x with respect to xi right there. So let's keep that solution there. Let's keep that solution there as a reference. And we also know that g of x is equal to 0, where all the constraints are equal to 0 vector. So that means that we're going to do the same thing right there. And through the transitive property, we know that that must be true. Alright, so essentially we have changed this from indexing to a matrix form. So elements in the numerator will vary across the rows, and elements in the denominator will vary across columns. So yeah. But one important thing to note is that in the constraints equation we have here, the partial derivative of gk with respect to xi, that one on the bottom. Think of index I as telling us which equation we are referring to. So I is going to be like a slice of this. All right, so So that implies that that is true. Alright, so we could solve for the partial derivative of hj as a function of the independent variables with respect to xi, that matrix right there, by taking the partial derivative of gk with respect to xj, that matrix inverse on both sides of the equation. Alright, so if we make a substitution of the constraints function equation that we got in matrix form into the top equation of that objective function thing that we got, then we get this equation over here. Then we can remove the parentheses. Alright, so we have switched back to index notation over here. So we went from matrix form to index form. And we're actually going to call that summation over j lambda sub k. And we don't know if that's a constant or if it varies across the x's. We don't know. But we'll call it lambda sub k. Alright, so now let's express this a bit more elegantly. So lambda sub k is equal to that summation right there over j. So essentially, we have a system of equations. We have a system of n minus m equations when we're defining the dependent variables in terms of the independent variables. Then we also have a system of n equations, which is the equation we got before of the partial derivative of f of x with respect to xi. So what we have here is a system of equations. Initially, our unknowns would be all variables in x, but if we substitute in the n minus m parameterized variables in x that we got from the constraints into the n equations in the box, then we have m unknown variables from x and n minus m unknown. Thus we have n equations and m plus n minus m, which is equal to n unknowns. This means that we can find unique values for all m independent variables in x and for all lambda k's. This must mean that the lambda k's are constants. So they're not functions of anything, they're just constants that vary with k. So since we have unique values for all the independent variables in x, we can find unique values for all the dependent variables in x using the equations in that one box where we have the partial derivative of f of x with respect to xi is equal to that summation over k of lambda sub k times the other stuff. So at this point, we have solved for all variables in x, as well as all the lambda k's. So we will call this unique solution x bar from that system of equations, and it represents the point at which the minimum slash maximum resides in f of x, subject to the constraints g of x is equal to the 0 vector. So note 4, we will switch to vector notation. And so we have g of x is equal to 0, that's a constraint in the top box, and the gradient of f of x is equal to the summation of k is equal to m plus m, sorry, not m plus m, m plus 1 all the way to n. We may also define a function called the Lagrangian, which we would call capital F, such that when the gradient of f is equal to the 0 vector, the following conditions are automatically satisfied, which were those two conditions that we need to solve for x bar. So to see this better, let's express things in index form. We want a function f such that when we take the gradient and set it to 0, which will be optimizing it to find critical points, it automatically satisfies the conditions below. The bottom condition on the left-hand side of the equation already looks like the elements in the gradient across the variable x of f of x. But what about that other condition, g sub k of x is equal to 0? Well, let's finish the gradient. Remember, we want the gradient across the variables of f of x lambda to be equal to 0. That means that the gradient across both variables of f of x lambda must be equal to 0. So that means that each element within the lambda gradient must be equal to 0, and g sub k is equal to 0. Therefore, g sub k must be equal to the elements, and the equation that satisfies these conditions is the Lagrangian, capital F of x comma lambda. Alright, now that is the end of this video, and thank you for watching. Now this video took a whole lot of brain power. I was like thinking about it for an entire week, so I put a lot of effort into this thing, so I would really appreciate it if you liked and subscribed to this video. So yeah, see you next time.